An inertial balance. How astronauts measure their mass in space. Let's talk about that. How do astronauts measure their weight in space? Well, they don't, because there is no weight in space. Weight is determined by mass times gravitational attraction of the Earth. And since astronauts are falling towards the Earth continuously, they feel weightless. Let's say you are standing on a scale inside of an elevator to measure your weight. You look down at the scale and let's say the readout says 180 pounds. Then let's say the cable to the elevator was cut. God forbid that. And you look down at the scale and it would read 0 weight. You would see 0 weight because you and the elevator are falling towards the Earth. You are essentially weightless until you hit the bottom. This is the same experience astronauts feel. That's why they float in space, although there is gravity at their orbit level or altitude. They are essentially falling around the Earth because they never contact the surface. Therefore, they are in a continuous free fall. So if weight is calculated by multiplying mass times gravitational attraction, but in orbit, astronauts don't feel or don't experience gravity, then how can mass be calculated? In order to accomplish this, we need an equation that does not involve gravity. So let's see how we measure mass. Weight is determined by mass times gravitational attraction of the Earth. On Earth, force is equal to weight, and weight is equal to mass times gravity. So therefore, the force of weight is equal to mass times g, or m times g. And if we solve this equation for mass, we get mass is equals force weight divided by g. But in orbit around the planet, we float in space. We float because we are continuously falling around the Earth. So our mass does not exert any downward force due to gravity, although gravity is very present. We need a method that does not involve a planet's gravity g, and does exert an acceleration on our mass while in space. There is such a force, and that force involves springs. So let's investigate springs. Okay, here we have a spring, and the equilibrium point of this spring is along this dotted line, to where this spring is not stretched or compressed. If we call a length of rod, we make a spring. If we pull this spring beyond this equilibrium point, it will exert a force we call a restoring force to return it to the equilibrium length. So if we pull this spring to the left, there's a restoring force to pull the spring back to the right. But once the spring goes back to the right, it will go past the equilibrium point and then oscillate back and forth. If we pull this spring further past 0, there will be a larger restoring force. This restoring force is proportional to the distance from equilibrium or displacement. F's restoring is equal to some constant k times the change in x. K is determined by the properties of the spring rod used to make the spring. Let's continue. So K is determined by the properties of the spring rod to make the spring. K is equal to E times A divided by L. E is called the modulus of elasticity of the metal used to make the spring. And the units on E is newtons per square meter. A is equal to, A right there, is equal to the cross-sectional area of the spring in square meters. L is equal to the initial length of the spring in meters. And the force of the spring force, is equal to K times delta X. And the force units is in newtons per meter. Delta L or delta X is equal to the change in length pulled past the equilibrium point, where newtons, N equal newtons, and M equals meters. Let's continue. Springs can't be stretched beyond a certain point or they will become deformed. This is called the plastic region. Just like a rubber band, if stretched into this region, it will break. So from this point here to zero, from zero to this point here, is the linear region, or where it's what's called an ideal spring. If a spring is stretched past this linear region, it goes outside the elastic zone, which is called the plastic zone. And if it's stretched a little bit further, it will break. So F is not linear in this region, but the rod will return to its original length here past the linear zone right here. So this part here is not elastic. It will be elastic, but it's not linear. In this portion is the plastic zone where the spring will be deformed. As long as the spring remains in the linear or elastic region, it's called an ideal spring and obeys Hooke's law. Robert Hooke was born in 1635, was an English scientist that stated if the pulling force does not exceed the spring elastic limit, then the length increment of the spring is directly proportional to its pulling force. Let's continue. The direction of the restoring force is always opposite the direction of displacement from equilibrium. So here's our spring, and that's where it's sitting without being pulled or pushed. If we stretch this spring, there's a restoring force. If we stretch this spring to the right, there's a restoring force to the left. If we compress this spring to the left, there's a restoring force to the right. If the spring is stretched, the force is to the left. If the spring is compressed, the force is to the right. Once the spring is released, it will oscillate back and forth around this equilibrium point until it settles again at the equilibrium point. Let's continue. This is how we determine the spring constant. Let's say we have a weight or mass attached to a spring, and it's just sitting there at the original length of the spring. A displacement causes the spring to exert a force towards the equilibrium point. So if we stretch the spring, it will oscillate back and forth. And that's called a delta force. Delta force, restoring force, is equal to K times the change in length. The change in force is equal to K times the change in displacement. So if we solve this equation for K, we get change in restoring force divided by the change in displacement. And if we plot this on a graph, on the left we have restoring force and on the bottom we have displacement. And if we plot different forces against different displacements, as long as we're in the linear zone, we get a linear line. Okay? And so, if we take the slope of this line, we get, for displacement of 0.21, we get a restoring force of 4.99. So, if we divide 4.99 by 0.21, we get K is equal to 23.76. Now, the more steep this line is, as this line moves to the left, we get a larger K. And as this line moves to the right, we get a smaller K. So the steepness of this line determines the value K, which determines a greater or smaller restoring force. And once we release this mass, it will oscillate back and forth. Okay. For instance, if the black dot was a pin right here, let's say that was a pin that went through this mass and was the ink part was on the white background. And if we could slide the white background down while a spring was oscillating back and forth, you would see a sine wave printed on the background, like this here. In physics, this gives an equation of displacement x. So we know in physics that x is equal to a cosine omega t plus phi. And you can see this is a sine wave or cosine wave. Sine wave and cosine wave is the same. If you stop this graph right here at this point at 1, it would be a cosine wave. If you stop this graph at 0, it would be a sine wave. So it's either x equal a cosine omega t plus phi or sine omega t plus phi. It doesn't matter. I just use cosine because I like working with cosine. So this is where x is equal to the displacement, a is equal to the amplitude, the height above equilibrium. Right here we have a as the height above equilibrium, and we also have a negative a, height below the equilibrium, because it oscillates back and forth. Omega is equal to the angular frequency, right there, omega, and t equals the time, where the phi equals the phase angle. Let's investigate this equation. So we know the restoring force. We also know that restoring force is equal to mass times acceleration. If we let a acceleration equal x double dot, we're just changing the symbol, x double dot, then mass times x double dot, which is acceleration, which is the second derivative of x, is equal to minus k times x. Therefore, x double dot plus k divided by m times x is equal to 0. If we solve this equation for kx and we move kx over to the right, we have mx plus kx equals 0. And we divide through by m, we get x double dot plus k over m times x equals 0. And since we know that b, equation b, x equals a cosine omega t plus phi, our previous equation, we can solve equation A. Let's continue. So we know the restoring force. If we take the derivative of A, we get the velocity. So here is A, equation A, x equals a cosine omega t plus phi. The derivative of x is equal to the velocity. So we get minus a omega sine, minus a omega times sine omega t plus phi. The derivative of cosine is minus sine. And the derivative what's inside the parentheses is just omega. If we take the derivative of the velocity, we get the acceleration, which is x double dot. And that's minus a times omega squared times the cosine omega t plus phi. Well, we know that a times cosine omega t plus phi is equal to x. Therefore, that's a minus omega squared times x. Therefore, our equation is, if we substitute x double dot equals minus omega squared times x in the equation, we get minus omega squared x plus k over m times x equals 0. And if we factor out x, we know that x times this quantity is equal to 0. Well, we know x is not equal to 0 because x is some value. So this value inside the parentheses must be equal to 0. And if that's equal to 0, we can solve for this part of the equation. Let's continue. Since we now know which term is equal to 0, we can solve for omega. So we set this term equal to 0, and we solve for omega. And we bring omega squared over to the right. We get omega squared equals k over m. And we take the square root of both sides. We get omega equals square root of k over m. And since omega is equal to 2 pi over t, the period, we get 2 pi divided by t equals square root of k over m. And if we solve for the period, we get 2 pi times the square root of m over k, where t is the period of oscillations in seconds. Now we have an equation involving mass without gravity. Now all we have to do is know the spring constant k and the time the oscillations in seconds for t. Let's continue. So now we can sit an astronaut on a spring and oscillate them back and forth for t seconds. As long as we know the spring constant, we can solve for the mass of the astronaut. So our equation says our t seconds of oscillations is equal to 2 pi times the square root of m over k. And if we solve for mass, we get mass of the astronaut is equal to k times the quantity t divided by 2 pi squared. So let's let k equal 23.55 newtons per meter. And let's say we set the astronaut on top of a spring and we oscillated him back and forth for a certain amount of time, and we counted 11.7 seconds of oscillations. So mass is equal to k times the quantity t divided by 2 pi squared. And since we know k, because we've determined that previously, that's equal to 23.55 newtons per square meter times the quantity 11.7 seconds divided by 2 pi, and all of that is squared. And if we perform that calculation, we get 23.55 times 3.47. So the mass of the astronaut is equal to 81.66 kilograms. Let's continue. So now we can solve for the mass of an astronaut by sitting him on top of a spring and oscillating him back and forth in space. And that's essentially the astronauts will sit atop a spring in space and vibrate back and forth for t seconds because of the lack of the experience of gravity, for what NASA calls microgravity. This is exactly how you weigh your produce on Earth in the supermarket. You sit your produce inside of a basket. Scale, and it vibrates back and forth until the needle centers on 0, or on the weight of your produce. And then you're charged for how much weight you have. And essentially, this is what astronauts do in space. They sit on top of a spring and they oscillate back and forth. And the equipment does what we just did and measured their mass. On Earth, you measure weight. In space, you measure mass. Here is a video of astronauts getting their mass on the International Space Station. And you'll see, essentially, they do the same thing we did here. Until next time, I hope you learned something.